All right, recording in progress, sounds like. Okay, so we were here. 6.4. I should finish 6.4 pretty quickly today. There were only 2 more problems, and I pretty much almost done the entire section. I might sneak in a little bit of 6.5, so we'll go ahead and do that if necessary. Okay, Thursday, so-called buffer day, I will reserve Thursday for question and answers. If you have any questions, you can bring it up then, but if not, I will just go ahead and continue on with chapter 7. Right, you should have gotten your quiz score back, and I sent out the quiz solutions also, right? If you didn't get it, let me know. Quizzes are out of 5, but of course, this Friday, we're not having a quiz, we're having an exam. Okay, so I'll talk quickly again about the exam. Coverage is chapter 6. So this is what you're responsible for. I give about 10 questions in a test. So if there's 5 sections, that would mean 2 questions a section would seem reasonable. And let's see, you are allowed to have 1 formula sheet, 1 piece of paper, 8.5 by 11, both sides. Put in anything you feel like on that cheat sheet, but that's it. So that's just the extent of your legally cheating, so to speak. You get 1 formula sheet, but no other books, notes, computer, people, internet, so on. Okay, you can have that 1 sheet. You must log on. So I know some of you are here, some of you are not. You're watching the video. I don't take attendance in general. I do take attendance on the exam, so you must join the exam. So in other words, don't think you can not join the Zoom call on Friday and just submit the exam and try to sneak it in. Oh no, I'll take attendance. Okay, so for the exams, you have to show up with the Zoom call that I gave you many times, and have your first and last name as on my row sheet. Don't let me guess who you are. Have your camera on. I won't be recording. True background. Don't have, artificial background, Golden Gate Bridge or space, outer space or something like that. True background. Keep yourself muted. And if you have any questions during the exam, just send it to me through the chat. And you get the entire time, so 8:10 to 9. I will send the exam on Canvas announcements, probably right around the top of the hour. So let's say right around 8:01, 8:02, something like that. Then you join me afterwards. Okay, there's a 70% homework requirement. You must submit at least 70% of the homework. In my opinion, that's really a joke because I end up doing a huge percentage of the homework anyway. Sometimes I end up doing 70% of the homework, so you just have to copy it all. And now that you've already had a couple of quizzes, you should know what to do. For the quiz and the homework, just get your cell phone and click, 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 take pictures. Or if you have a scanner, make it look better, scan it, and email me your exam and also email me your homework. Okay, so let's see. And yeah, if you haven't already done so, show me a picture of yourself with your ID. Again, for a class like this, I don't get to know what everybody looks like. So I just want you to send me an ID. If it's your driver's license and you don't want me to see your, age and height and weight and birthday and address and all that stuff, just black it all out. All I need is your name and your picture. And you can just blacken out everything else. Okay, and then, so I'll watch you on Zoom. Class ends at 9 o'clock, so you have the whole 15 minutes to do the exam. I'll close the Zoom at 9. So you have 5 minutes after that. So you have until 9:05 to submit the exam and until 9:30 to submit the homework, 9:30 a.m. But if you want to submit the homework early, you may submit the homework early also. Okay. All right, so that's what I have to say about the exam. Anybody has any questions about the exam, you can ask me now or put it in the chat, or you can do it later also. Okay, then let me go on and finish up 6.4 and maybe sneak in some of 6.5, and then that's pretty much about it for today. So we might end fairly early today, but not sure. We'll see how it goes. Do we have to print out the questions for the exam? No, you don't. I know what the questions are. Just don't waste your time with that. Go straight to it. Now, if you want to print it out for your own benefit, you may. Sometimes students like to have the actual questions there. I mean, that's the way it is face to face. But on the other hand, I know some of you don't even have a printer. So you can just look in Canvas announcements for the exam and just work it on a sheet of paper and then just take pictures of your cell phone and go from there. Okay. All right, so I think that's it. Let me go ahead and knock off the last couple of problems I had from 6.4. I talked about problem 15. Now let me go ahead and formally finish it up. Get this out of my way. A cable that weighs 2 pounds per foot is used to lift 800 pounds of coal up a mine shaft 500 feet deep. Find the work done. Problem 15. Okay, so I gave you hints last time, but this time I'll go ahead and actually finish it up. So let me see where we are. So last time I kind of covered it up. Want you to try it on your own, but now I'll uncover it up. All right, so we have a cable that's 2 pounds per foot. That's almost like the rope problem from the problem 13. Here's a delta X, 500 feet. The other problem was 50 feet, but other than that, it's just a plug-in. And there's 800 pounds of coal at the bottom. Okay, so I have the work for the coal. That's just like the gorilla problem. Constant force, constant distance. So it's 800 pounds, all moving up 500 feet. So that's 400,000 foot-pounds. Work for the coal. Remember the gorilla problem? It was force times distance, just 360 pounds. Okay. Weight is a force. It's a force down toward the center of the earth times the distance. So that's the coal. The coal is like a gorilla problem. Now the work for the cable, you work it out just like this one here. So slice delta X. My delta W, little change in work, is ticket density 2 pounds per foot. How many feet do I have for that little slice, delta X? Okay, the feets cancel out. And then this piece of cable is all moving up a constant distance, X. Again, it's not really constant. The top and the bottom are slightly different, but as delta X approaches 0, which is what's happening in the integral, okay, then it's really the same thing. So 2 pounds per foot times delta X feet, feet cancels out, times X feet, so your units are now foot-pounds, so you have it right. So that gives me 2X delta X, 2X delta X foot-pounds, and that's what I'm integrating. Right, so the work for the cable is the integral from 0 to 500 of 2x dx. Right, integral of 2x is x squared, because the derivative of x squared is 2x from 0 to 500. Okay, plug in 0, you get 0. Plug in 500, you have 500 squared, which is 250,000 foot-pounds. All right, so we just add the two up. So the total work is the work for the coal, 400,000 foot-pounds, plus the work for the cable, 250,000 foot-pounds. So a grand total of 650,000 foot-pounds. Okay, so that's the answer to 15. So that's how you break this up. You have the constant part, just like the gorilla problem. All the coal is moving up same amount. Constant force, constant distance. And what's not constant is the cable. It's like the rope where you're pulling up the rope. They're not all traveling the same distance because the top doesn't have to go as far as the bottom. For the coal, we're assuming it's all moving up the same. So I just add the two. So the final answer is 650,000 foot-pounds. Okay. All right, so that's 15. And the last one I need to show you is problem 23, although that's a little bit harder problem. So here's 23. A tank is full of water. Find the work required to pump the water out of the spout. Okay, and it's exercise 25 and 26. We're not doing that, so don't worry about it. Okay, so here's this trough-like thing. Looks like this. It's all full of water. This is 2 meters. This is 3 meters. This is 3 meters. It's 8 meters deep, and all the water is going up here. Okay, now I can't draw. I'm not an artist, but I can do the cross-sectional part, and that's all I need. I'm not going to draw the 8. I just know in the back of my mind there's an 8 there. So I'm going to only show you this thing right over here. Okay, so this is just the front. So this is the same thing. That's all I can draw. 3 meters there, 2 meters up, 3 meters across, and it's 8 meters deep, which I didn't draw. Okay, that's that 8 meters there. If you only look at the front, there it is. 2 meters up here, 3 meters here, that's that 3 meters, 3 meters across, and it's 8 meters deep. What I really want to do is get rid of the book and go over the analysis. All right, so some things that I noticed. Therefore, from here to here is 5. This is 5 meters. Right. Now, I decided to call x equals 0 at the bottom. This is x equals 0, x equals 3. And I take a cross-sectional slice like so. Again, why do I slice like this? Because all the water molecules here are moving up the same amount, same distance. If I take this slice, again, I'm taking a quote-unquote sandwich of water. Okay. This almost rectangle, it's not a true rectangle, but it's almost a rectangle. And if delta x is very, very small, it looks more and more like a rectangle, right? You can't tell the difference, so to speak. All right, now by similar triangles, they said this is 3 and this is 3. Therefore, if I call this x, this is also x by similar triangles. Okay. The ratio of the height and the length is 1 to 1, 3 to 3. So this is 3 and this is 3. Therefore, if this is x, this is also x. So in the final analysis, I'm going to integrate from 0 to 3. Now, if this is x, this is 5, the distance is 5 minus x. Okay, so all of the water molecules in this slice have to move up 5 minus x meters. Okay, so how far do these water molecules have to go up, and what's the work involved? Right. So we worked this out kind of like the aquarium problem. So my delta W, my change in work, is 1,000 kilograms per meters cubed. I need to get rid of meters cubed. Well, volume is meters cubed, so length times width times height. Okay, I know it's 8 meters deep. I can't draw it, but the book had it, right? So I know one dimension is 8. Problem 23, right? 8 meters across. So 8 meters by x by delta x meters cubed. So that slice, that sandwich of water is 8 by x by delta x. Meter times meter times meter is meter cubed. See, that way I can cancel that meters cubed with that meters cubed. So this 8x delta x, that's the volume of that slice. I know, maybe I'll write that down. Volume of slice. So right now I have kilograms. That's a mass. How do I change it to force? Multiply it by the acceleration due to gravity on Earth, 9.8 meters per second squared. Right, so 1,000 kilograms per meters cubed. So how do I get rid of meter cubed? Multiply by volume. Meters cubed cancels meters cubed. So 1,000 times 8x delta x. I now have kilograms multiplied by acceleration due to gravity, 9.8 meters per second squared. And of course, right here, this is mass. So the mass of water would stay the same wherever you are, but the weight would not be the same, right? It depends on what heavenly body you're on. Of course, we're on Earth, so 9.8 meters per second squared, okay? Now, if you were doing this experiment on the moon, like the Apollo astronauts in the 1960s and 1970s, well, it doesn't weigh as much because it's a smaller acceleration due to gravity, okay? And if they were having something like the rovers on Mars, Mars has a different acceleration due to gravity, right? Or if you're in an International Space Station, the acceleration due to gravity is 0, so your weight would be 0. But in all situations, you have the same mass, we said, right? So 1,000 kilograms stays 1,000 kilograms on Earth, on Mars, on the moon, or even if you're floating around in space, it's still 1,000 kilograms, but the weight would be different. All right, so now we have a force. Work is force times distance. What's the distance that all of these water molecules are traveling? 5 minus x. All right, so we finally have everything that we need. Again, my suggestion is your head might be spinning. I don't understand anything that's going on. If you understand it, great. If you don't understand it, put down sample problems, see if you can reconstruct this in case I ask something just like that during the test. And by the way, yes, you are allowed to put sample problems on your formula sheet, on your cheat sheet to guide you, saying, you know, how do we do this problem, right? And say, oh yeah, it looked like this problem, and then just kind of mimic what happened there. Oh yeah, we did this over here, that one over there, and whatnot, right? Okay, a little bit of units analysis here. This is kilograms, meters per second squared, which is newtons. Okay, meters cubed cancels, kilogram, meters per second squared. In the metric system, that's a newton. We're traveling meters, so we have newton meters, and newton meters gives me joules, Joule. All right, so I'm going to multiply all this mess out. 1,000 times 8 times 9.8 is 78,400. There's an x, there's a 5 minus x, and a delta x, joules. Okay, so this is a total work in taking that slice of water, and it all moves up 5 minus x. So that's what I integrate. And so once I have that slice, then I make it all travel the same distance. So I'm just going to integrate 78,400 x times 5 minus x. Delta x becomes dx. So that's dx. And I'm integrating from 0 to 3, this water from 0 to 3, not 0 to 5. The water is coming up to here, okay, but there's only water from 0 to 3. Integral from 0 to 5 would be the trough is such that the spout is right up at the top. In other words, if you integrate from 0 to 5, then this thing would have to come all the way up to the same level as the spout. That would be integral from 0 to 5. That's the reason why we only integrate from 0 to 3. We're only going here because there's water from 0 to 3. Okay. All right, let's see. 78,400, distribute 5x minus x squared. 78,400, 5x squared over 2 minus x cubed over 3 from 0 to 3. Plug in 0, you get 0. Plug in 2. So, plug in 3. 3 squared is 9. 9 times 5 is 45 over 2 minus, plug in 3. 3 times 3 times 3 is 27. 27 divided by 3 is 9. So 45 over 2 minus 9. Common denominator is 2. Grind it out. 1,058,400 joules is my final answer. And that is that. All right, so now I'm done with 6.4. So I can check this off. I've got up to here. All that's left is 6.5. It's really not that bad a section. Something called the average value of a function. And the more challenging problems were probably over here, but 6.5 average value of a function, hopefully it's not too bad. Okay, so I'm on par if I were to stop right now, but I'm not going to stop right now. It's better to just go ahead and get a little bit ahead in case I fall behind later or I get sick or my internet goes down or whatever. So I'm going to sneak in a little bit of 6.5. We'll probably still end a little bit early. Okay, so 6.5 is an average value of a function. And we had to do what? 1 to 17, I think it was. So let me show you the problems for the benefit of those of you who don't have the book. You're not getting it. Seem to be getting a frog in my throat there. Page 463. That. And that. And that. And 17. And that's about it. Okay, so you've got the homework. All right, so average value of a function. Now, if we have a finite number of values, we know what the average means, just add them up and divide by how many you have, right? Like you say, we have 5 tests. What's my average score? We'll just add them up and divide by 5, right? In general, if you have n numbers, we'll add them up and divide by n. What do you do if you have infinitely many temperatures, though? So you have a graph, like average temperature in one day. Okay, so here's a 24-hour time frame. Okay, and every hour, every time has a temperature, right? But that's not a fixed number of points. There's infinitely many points, right? There's infinitely many times, on a day, starting at 12 midnight, 0, all the way to the next day, 24 hours later, right? So it's not just a set finite number of values. Right? You have a curve. At any point in time, any real number between 0 and 24 has a corresponding value. So how do I find that average value of such a set? Well, they have a proposal over here. Something should be clear. I wouldn't take the biggest number. That's not fair. I wouldn't take the smallest number. That's not fair either. Right? So intuitively, we would say, okay, average value is somewhere in the middle, right? So this is how the temperature goes during the day, right? So from midnight to 6 a.m. it drops, and then the sun comes out, and then it goes up and up and up. And then 18 hours, that would be like 6 o'clock. Then the sun sets, so the temperature starts to drop again, right? Up until 24 hours until the next midnight. So here's a graph of temperature versus time, right? From 12 to 6, it goes down. Then the sun comes out and temperature goes up, and then the sun goes away, and then the temperature starts to fall again. So the average temperature is, quote unquote, somewhere here, right? So what do we mean by somewhere here, right? How can we make it more formal? Take a look at this picture right here. It looks like they're doing something with the area under a curve, right? So let's say this is a function. It doesn't have to be temperature, it's something. We're calling this the average value. We're going to define the average value so that the area under the curve, I'll trace it out, matches the area of this rectangle. That does seem reasonable. It's almost as if to say, if I cut out that area and place it here, I get the exact same amount, right? It's not fair to take the top. It's not fair to take the bottom. It's somewhere in the middle. And what do we mean by somewhere in the middle? We're going to define it so that the area under the curve that I trace out with my pen turns out to be the same as the area of this rectangle. So getting back to the temperature graph, the integral of the function should match this area under the curve. So we know how to find the integral. This is just a rectangle, base times height, right? So we have the height, t average, and the delta x. In this case, it's b minus a. Right, so if I have the area is t average times b minus a, if I divide by b minus a, I get an expression for the average value. And here it is. Okay, so put this on your cheat sheet, on your formula sheet. It's on page 461. F average, and just so you know, I like to write AVG for average. They put AVE. To me, AVE sounds like avenue, so I use AVG for average. But if you want to use AVE, that's fine. 1 over b minus a, integral from a to b of f of x dx. Okay, so that's our definition of the average value of a function. Okay. One way you can think of it is area divided by width is the average height for positive functions. Okay. That kind of matches area as length times width. Right. So that's easy. All you got to do is integrate, but make sure you divide by the length of the interval. In fact, I'll just go ahead and tell you from my experience, A lot of times students will concentrate on the integral, which is great, and then you forgot to do this part, the 1 over b minus a. Okay? Or it's like saying divide by the length of the integral. My suggestion is put this down once and for all before you get started with the problem. Get this down, it's there, and then you can work on the integral. Okay, so in other words, sometimes students do the hard part and you forget the easy part to multiply by 1 over b minus a. Okay, so that's what we got. And here's my interpretation of it. Average value of a function. Here's a, here's b, here's some function. What do we want to call the average value, f average? Again, I'm using AVG for average, not AVE. I want the area of this rectangle to match the area under the curve. What's the area of the rectangle? Base times height. The height is f average. How far is it from A to B? Well, B minus A. Right? Like if this is a 3 and this is a 10, you would just say, oh yeah, 10 minus 3. So I want f average times B minus A to be the same as area under the curve, integral from A to B of f of x dx. Divide both sides by B minus A, and it looks like this. So again, put this on your cheat sheet. It's the same as what I showed you in the text. F average is 1 over B minus A, integral from A to B of f of x dx. Think of it as integral divided by length. Now, we usually write it this way. So how come you don't write it as divided by B minus A? You could, but that looks kind of funny to have an integral on top of a fraction, right? So to me, it looks too quirky to divide by B minus A. So we'd rather say multiply by the reciprocal, multiply by 1 over B minus A, but it's the same thing. And then integral A to B f of x dx. Okay. That's the way it looks. All right, so it's only about 8:40. I was going to show you, I'm going to call it 1 star, which means this is not the actual number 1 in our book, but it was in the previous edition. But we're learning how to do stuff anyway. Okay, so next time I'll get started with problem 5 now that we have the formulas down. But I think you'll agree this section is really not that bad. Okay, the harder questions on this chapter would be the this method, the shell method, the techniques of integration, stuff like that. Okay, suppose you have the function f of x equals 4x minus x squared between 0 and 4. What's the average value of the function? Okay, by the way, you don't actually have to graph it. I did just for teaching purposes, but ignore the graph for a moment. Average value is 1 over the length. So what's the length of the interval? 4. 1 over 4 minus nothing. So that's what I mean by put it down, then you can worry about the integration. Because sometimes students will forget to do that 1 over b minus a. So I advise you just put it down once and for all, 1 over 4 minus 0. Then you say, okay, I know I got to multiply the answer by 1/4. See how I just carried the 1/4, 1/4, 1/4, because I already saw it, right? But if you focus on the integral, you might get so involved with the integral, you might forget to put the 1 over 4 minus 0, right? So that's why I say do that first, 1 over 4 minus 0, and it's there. Now I integrate 4x minus x squared from 0 to 4. And that's pretty easy. Okay, so I have the 1 over 4, 1 over 4 all the way through. Okay, integral of 4x squared over 2, 2x squared, minus x cubed over 3, from 0 to 4. And see, now that I have the 1/4, right? Hopefully you won't forget it. It's a little reminder to say, oh yeah, I got the 1/4. I carry the 1/4 all the way through. All right, plug in 0, you get 0. We like plugging in 0. Plug in 4. 2 times 16 is 32. Minus 4 times 4 times 4 is 64. 64 over 3. 32 over 1 multiplied by 3 over 3. So 1/4 of 96 minus 64 over 3. Okay, that's 32 over 3, and a 4 on the bottom. 32 divided by 4 is 8. Final answer is 8/3. So the average value is 8 over 3. Okay, the problem's finished, but here's the graph. It's a parabola opening down because of the negative. When you plug in 0, you get 0. when you plug in 4, you also get 0, don't you? Plug in 4, 16 minus 16 is 0. It looks something like that. And there's the average value. And please notice the average value is not halfway between the maximum and the minimum. In other words, the highest number is 4, the lowest is 0. You might say, oh, the average is 2. No, it's not. Okay, so it does not have to be exactly halfway. It could, but it doesn't have to be. The average looks like it's 2 2/3 in this particular case. So what is that average value? We're saying the area under the curve, right? See how I'm tracing out this parabolic region is going to be the same as the area of that rectangle. Okay? So I guess that would mean, for instance, if I divide, let me get my ruler right there, this area would exactly fill up the hole here, so to speak, and this area here would fill up that hole there so that you get the same amount of area in this particular situation. Okay. Right, so don't just take half of the maximum value. That does not have to be, in general, the average value. 8/3 is what, 2 2/3? So it's more than halfway up. Okay. All right, folks, it's not even 8:45 yet, but I was done for the day. So if anybody wants to ask me questions, you may, otherwise we would finish. Okay, so I have 2 more days to knock off the rest of 6.5. I might even finish tomorrow. If that's the case, I'll just go ahead and try to be ahead in case I fall behind later. I'm reserving Thursday for questions and answers. So if you want to ask questions on Thursday, you may. And by the way, that includes those of you who normally don't join. If you normally don't join, if you want to come just Thursday to ask questions, you're allowed to do that. But you don't have to still. Okay, but everybody has to show up to the Zoom call on Friday. You must show up then. So that's the only required attendance. All the other attendances are not required. You can always just watch the video later. Okay, let me stop the share and check the chat. If anybody has anything there. Okay, nothing extra there. All right, anything else, please? Otherwise, we're done. All right, seeing nothing and hearing nothing, we're going to call it a day. All right, everybody, have a good day and see you next time. Okay, bye, everybody.
Thank you, Professor.
Thank you.
Take care. Thank you.